Hello everyone. In today's video, we will walk through another sample problems in determining the maximum moment in beams, which is part 3. We also cover the following key points in determining the support reactions, draw the shear force and bending moment diagram, then explaining the simplified approach and provide tips to quickly identify the maximum bending moment. So let's dive into our problem. Determine the maximum moment of the beam carrying a uniform load and a concentrated load as shown in the figure below. So in the load diagram, we have here the beam, we have the cantilever end, and it is subjected to 35 kilonewton concentrated load and a 16 kilonewton with the spaced at 1.5 and 2 meters, 1.5 and 2 meters cantilever end. Now let's get started with our solution. First of all, we need to determine first the reaction at the support before we can draw the shear and moment diagram. So to determine the support reactions, we need to sum up moment at point A at any location or B. So summation of moment at A is equal to 0. Then minus RB times 5, that is counterclockwise, times the moment arm, which is 5, plus the 35 times 1.5 is the one here, plus 16 kilonewton times 3.5, plus the uniform load of 25 kilonewton per meter times the distance, which is 2 meters, times the centroid or moment arms from the center of the load to the point A, which is equal to 2 meters over 2 plus 5, and that is equal to 0. So to solve the reaction at B, that is equal to 81.7 kilonewton. Now we need to determine the reaction at point A. So by summing up forces, positive along y-axis, let's say is equal to 0, we have 81.7 kilonewton, which is the reaction at the support B, plus RA minus 35 downward load minus 16 kilonewton here, minus the 25 kilonewton per meter, that is the uniform load, times the distance of 2 meters is equal to 0, and that is equal to 19.3. Now we have determined all the reactions at the support. We can now proceed to draw the shear diagram. So to draw the shear diagram at point A, that is from 0 plus the reaction at A is equal to 19.3. So the shear at point A is equal to the reaction at this point. So the shear at point C, that is equal to 19.3 kilonewton minus 35 kilonewton, that is a dropping load. Now that is equal to negative 15.7. So take note guys that between point A to C there is no load, so our shear here is constant. Meaning to say, if you cut any section between A to B, the shear is 19.3, that is constant. So at point C, our shear at this point is 19.3. Then we have the negative 35 kilonewtons. That's why we have minus 17.7. So from C, point C to D, there is no load, so it is constant. Then just to the right of point D, we need to subtract 16 kilonewtons from 17.7. That's why we have negative 31.7. So that is shear at D, negative 15.7 kilonewton minus 16 kilonewton, that is equal to negative 31.7. So from D to B, there is no load. That's why our shear here at this between this point is constant. Then we have to add negative 31.7 plus the reaction at point B, that is equal to 81.7. So the total is that would give us point B minus 31.7 plus 81.7 kilonewton, that is equal to 50. So to go up, positive 50 here. Now, at point E, that is equal to 50 minus 25 times 2, and that is equal to 0. So here guys, the between B and E, the load here is uniform. Then in our shear diagram, this is linear. But here there is no load. That's why we have a constant shear force here. Meaning to say there's no load in between. Now we can proceed to draw the moment diagram. So to draw the shear or the moment diagram, the maximum moment can be determined by calculating the area under the shear diagram, starting from the point of zero shear. So if we have the load here, this is our shear diagram. The moment diagram, let's say at point A, we'll start from point A. The moment at point A is equal to 0. Then moment at point C is equal to the area to the left. Our shear here is positive. So the moment is equal to 19.3 kilonewton times 1.5. So 19.3 times 1.5. So that is our moment at this point. That is maximum positive moment because the shear here is 0. The maximum moment occurs where the shear is 0. So at moment at point D is equal to 28.95 plus the area of the shear diagram between point C to D. So that is point D 28.95 minus 15.7 times 2, which is this one here. 15.7 times 2. So that is equal to negative 2.45. So at the moment at point B, that is equal to minus 2.45 kilonewton meter minus the area between D and B. So that is equal to 31.7 times 1.5, and that is equal to minus 50 kilonewton meter. This one we have negative 50. So the moment at point E, obviously that is 0 because there's no moment at that point. So negative 50 kilonewton plus the 0.5, the area of the shear, times 50 times 2, area of the triangle, and that is equal to 0. That is the moment at this point, 0. If it is not, if it so happen that it is not 0, meaning to say you need to double check your calculation here. It is normal if the difference between let's say 0.01, 0.02. That's normal because that discrepancy is due to the rounding up of numbers. So the final result, guys, the maximum positive moment that is equal to 28.95 and the negative moment that is 50. That's the maximum moment, is the governing one. So when you draw the shear the moment diagram, uh, if the shear is constant, the moment here is linear, first degree. So we have here constant, we have here linear. This one is constant from point D to B, linear. But from point B to E, we have the linear shear. So our moment is second degree, which is parabolic. So from this point, moment here is positive slope until it reaches to moment is zero. So if the shear is positive, the moment diagram is positive slope. This is negative shear, negative slope, which means downward. Negative shear here between D and B, so we have negative slope. Here is positive, so positive slope going up. So that's all, guys. That's the end of our video today. Please, if you enjoy this video, please don't forget to like or consider subscribing so that you will be updated for the next upload. Thank you very much. See you next time. Bye bye and God bless.